Hydrogen. You hear about it all the time now, right? It's often called the key fuel for really deep decarbonization. That missing piece in the whole power to X puzzle, essential for tackling those tough sectors, think heavy industry, aviation, shipping. And given that the global energy system is responsible for, what, over 73% of greenhouse gas emissions, figuring out how to make reliable, low-carbon hydrogen at scale, well, that's the mission. What the industry calls baseload supply.
Exactly, and that's precisely what we're diving into today. We've got some fantastic source material here. It gives a really comprehensive, forward-looking analysis of what this looks like in practice. So our mission is to break down the environmental side, the tech trade-offs, and maybe some unexpected issues identified in this study. The full title is Prospective Life Cycle Assessment of Baseload Hydrogen Supply Based on Solar Photovoltaics and Wind Power, including Underground Hydrogen Storage.
Okay, yeah, that is a mouthful, but I guess the depth is needed because the focus here is huge. This study, it looked at the future environmental impacts of making greeny hydrogen, so hydrogen made only from renewables. And importantly, using a completely self-contained off-grid system, that means solar panels, wind turbines, an electrolyzer, and these massive underground storage systems all working together.
And crucially, it didn't just look at one place. It modeled 4 very different countries: Finland, Germany, Spain, and Chile. This was to capture, the different mixes of sun and wind they have, and also the different geological needs for storage. And they assessed the impacts not just now, but looking forward from 2020 all the way up to 2050. That comparison across regions is, well, it's vital.
And the method they use sounds powerful: Prospective Life Cycle Assessment, PLCA. So this isn't just looking back at current emissions data, is it? It's about looking forward.
That's exactly right. PLCA integrates these really detailed future scenarios. It tries to anticipate things like better solar panel tech, more efficient electrolyzers, and maybe most importantly, the gradual cleaning up the defossilization of the supply chains that actually build all this equipment in the first place.
Okay, so let's get into those strategic decisions. Making green hydrogen means electrolysis. Now, this study specifically chose alkaline electrolysis AE. Why go with AE over, say, PEM, proton exchange membrane, or even SOEC, especially when PEM is often seen as more efficient right now?
Yeah, that's a great question. It really comes down to thinking about the long-term global feasibility and just raw scalability. The choice for AE was almost entirely driven by worries about critical raw materials. PEM, while efficient today, faces this potential bottleneck when you think about scaling it up globally because it needs platinum and especially iridium.
Ah, iridium, that's the one you hear about. What does that constraint actually look like? I mean, in practical terms.
Well, current estimates suggest the global supply of iridium could basically cap how much PEM capacity we can add each year worldwide, maybe around 50 electrical gigawatts per year. But if you think about what's needed for a massive power-to-X economy, we're talking needing to deploy hundreds of gigawatts every single year.
Wow, okay, that's a huge difference in scale. So the study is essentially saying, look, iridium supply is a potential hard ceiling for PEM, making AE the more pragmatic choice for massive global deployment, even if it means slightly lower efficiency to start with.
Precisely. They opted for the technology pathway they believe can actually deliver baseload hydrogen on a planetary scale without hitting that specific material wall.
Right, makes sense. So they picked AE to avoid the bottleneck. Now, what about the rest of the system? What specific bits of hardware did they model for this big off-grid setup?
They went into quite a bit of detail on the future supply chain. For electricity generation, they included 3 key types of solar PV tech. You've got the current standard modules, then the next-gen improved ones like TOPCon, and then the really futuristic stuff, perovskite on silicon tandem cells, the Perovskite tandems. These are expected to be game changers for solar economics because of potentially massive efficiency jumps.
That level of detail really underlines the prospective part of the PLCA, doesn't it? Thinking ahead about tech evolution.
Absolutely. And for wind, they modeled modern direct drive asynchronous generators, the kind of becoming standard now for big projects. Yeah. But the really structurally novel part, I think, is integrating the large-scale storage. Because remember, this system has to provide baseload hydrogen, 24/7 reliable supply. You can't just rely on when the sun shines or the wind blows.
Right, you need a massive buffer, turning variable renewables into something dispatchable, like a traditional power plant.
Exactly. So they built in specific underground storage options tailored to the geology of each country. For Germany and Spain, where you have suitable salt deposits, they modeled salt caverns. These are great, big, flexible, fast response. For Finland and Chile, where salt geology is rare, they modeled lined rock caverns. Maybe a bit more complex, but necessary. These storage options are just essential to get the continuous, reliable hydrogen flow that industry needs. Okay, let's shift to the headline results, the environmental impact. If you look at global warming potential over 100 years, GWP 100. The data shows a really significant improvement everywhere they looked. The GWP 100 values per kilowatt hour of hydrogen produced, they dropped from a range of roughly, say, 31 to 47 grams of CO2 equivalent back in 2020, down to a much lower and tighter range of 12 to 16.5 grams of CO2 equivalent by 2050.
Wow, okay. That's like a reduction of roughly 60% across the board. But this is where the country comparison gets interesting, right? Let's look at Chile versus Finland. Chile, which the model gave 100% solar PV because of its amazing Atacama Desert sun, it achieved the absolute lowest GWP 100 by 2050. Just 12 grams CO2 EQ. That's a huge 71% drop from its 2020 baseline.
Right. Now contrast that with Finland, which is modeled with mostly wind 80% share. Finland actually started with a lower GWP in 2020. Sometimes wind systems look better initially because the materials like steel and concrete might come from less carbon-intensive grids at the start. But Finland's overall reduction by 2050 was smaller, only about 48.6%.
So why does solar seem to pull ahead so much in the long run, according to the study? What's driving that?
It really boils down to the anticipated technology improvements. The study projects that the efficiency gains, and therefore the reduction in materials needed per unit of energy, especially from those advanced PV types like the perovskite tandems, those gains are expected to be more dramatic than the improvements in wind turbine tech over the same period. Basically, by 2050, the idea is solar panels will be so efficient that the amount of stuff needed to build them, relative to the power they generate, will be significantly less than for wind turbines. Got it. So it's not just about having more sun hours, it's the projected leap in solar cell efficiency that really helps Chile lower its GWP so much by 2050. Exactly right. Now, let's pivot to another crucial climate metric, GWP 20. This looks at the impact over just 20 years, so it really highlights short-term warming effects. The finding here is, well, it's pretty sobering. The GWP 20 values are consistently higher than the GWP 100 values. By 2050, they're about 17.5% to almost 18% higher across all 4 countries.
Hang on, a 17 to 18% difference. That feels like a really big gap for something meant to be green hydrogen. What's causing that discrepancy? Why is GWP 20 so much more sensitive?
It comes down to leakage, specifically the near-term warming impact of leaked gases. We have to remember, hydrogen itself isn't a direct greenhouse gas like CO2, but it acts as an indirect one. When it leaks into the atmosphere, it reacts chemically and actually increases the concentration of other potent warming agents, particularly methane and water vapor, high up in the stratosphere.
Okay. So hydrogen leaking doesn't trap heat itself, but its chemical reactions in the air cause other things to trap more heat, especially in the short term.
That's the mechanism. And the GWP 20 metric is much better at capturing the immediate, powerful warming effect of these short-lived influences. Methane leakage from any natural gas infrastructure is still lurking in the background, and crucially, the hydrogen leakage itself. GWP 100 kind of smooths that short-term punch over a whole century. So this finding really tells us, look, if we're going to build a massive hydrogen economy, controlling leaks has to be a top priority. We can't afford significant short-term climate damage from leaky systems.
That naturally leads to the big question, the one that often comes up with green tech. If these systems are running on 100% renewable electricity by 2050, why aren't the emissions zero? Where are those remaining 12 to 16 grams of CO2 equivalent actually coming from?
Right, and that's key. We've essentially gotten the operational emissions down to near zero. The remaining emissions, the hotspots, are all about the embedded carbon. It's the carbon footprint from the life cycle of the materials used.
So it's the footprint of actually building the wind turbines, the solar panels, the storage caverns, the electrolyzers themselves?
Precisely. The leftover greenhouse gas emissions are mainly from producing the bulk materials needed. Think steel for turbine towers and electrolyzer stacks, silicon for the PV cells, concrete for foundations, aluminum used in frames and components. Even with the future decarbonization scenarios they modeled, the global supply chains for these basic industrial materials are still projected to use some fossil fuels in 2050.
It's kind of humbling, isn't it? You can build a 100% renewable power source, but those last grams of CO2 are locked up in the global markets for steel, silicon, cement.
And there's a second major source, transportation. You have to account for the fossil fuels burned in ships and trucks. For example, getting those solar panels shipped all the way from manufacturing hubs, say in China, to installation sites in Chile or Spain. That global logistics network is still modeled as being quite fossil fuel dependent in the background system.
Okay, so beyond just CO2 or GWP, this study also looked at wider environmental impacts using those complex recipe indicators, things like human health, ecosystems, resource depletion. Was it all positive news there?
Mostly positive, yes. Alongside the big drop in GWP, they saw overall improvements between 20% and 53% across human health impacts, ecosystem quality, and resource use, which is great. However, there were a couple of minor but important negative trade-offs, areas where things actually got slightly worse.
Okay, what were those trade-offs? Where did impacts increase?
They saw slight increases in acidification potential and human toxicity impacts. And again, it traces back to those upstream material production processes, mainly metal extraction and processing. For example, nickel is important for the alkaline electrolyzers. Mining and processing nickel can release sulfur dioxide, which causes acid rain, contributing to acidification. Similarly, making steel and aluminum, even in cleaner future scenarios, can still release heavy metals that add to human toxicity indicators.
It really highlights that classic systems view, doesn't it? You solve one major problem, like operational carbon emissions, and it reveals these underlying issues in the industrial base, like pollution from metal production that now need tackling.
Absolutely. And what's also fascinating is how the different components contribute. Despite being huge, complex structures, those underground storage facilities, the salt caverns and lined rock caverns, they actually contribute less than 5% to the overall GWP, are relatively clean from a carbon perspective once built. The real drivers pushing the GWP down the electricity supply part are those technology leaps we talked about, adopting bifacial PV modules that capture light from both sides, and critically, that jump in AE electrolyzer efficiency projected to go from about 62.5% in 2020 up to 70.0% by 2050.
Yeah, that 7.5 percentage point gain in electrolyzer efficiency is huge. It directly cuts how much renewable electricity you need to make each kilo of hydrogen. Okay, so let's try and summarize the core learning here for you, the listener. The future for green baseload hydrogen looks, well, pretty promising. It seems to be driven largely by big expected improvements in solar PV tech and cleverly integrating large-scale storage. But, and it's a big but, hitting truly near zero emissions isn't automatic. It completely depends on cleaning up the industrial sectors like steel and cement and the transport sectors that actually build and deliver all the necessary infrastructure.
And this really detailed look at the future environmental footprint of baseload hydrogen, comparing different regions and technologies out to 2050, was provided by the study titled Once More, Prospective Life Cycle Assessment of Baseload Hydrogen Supply Based on Solar Photovoltaics and Wind Power, including Underground Hydrogen Storage.
Which brings us to our final provocative thought for you to chew on. This study makes it pretty clear that the final step to near zero emissions relies on getting to 100% renewable energy for making materials like steel and for running global transport. So what specific global policy or maybe investment push think about things like mandates for green steel or maybe international subsidies for e-fuels in shipping what needs to happen first to really speed up that final step towards zero emissions? And who needs to take the lead? Something to think about. Thanks for diving deep with us today.